Okay, guys, I'm in my house, so I wanted to just kind of let you guys know I'm not in the classroom anymore. I'm in the house. I have the board up on the screen. I bought a whiteboard, and so I put it against the wall. And hopefully it's not too dark. I'm going to check this video later, see if it's too dark in here. I'll turn on some more lights, but it's a little bit of a glare. You can probably already tell there's a little glare there. And I'm trying to see if I can reduce that a little bit or something like that. But let's get started. Let's pray. Father God, we thank you, Lord, for this day. We thank you, Father God, for your goodness, Lord. And we pray, Father God, you bless this time. Make this time yours, Lord God. We pray, Father God, you guide us in this day to be what you have it to be, Lord. In Jesus' name, amen. All right, so let's get started. We're going to be in section 5, chapter 5, bouncing around a little bit. Section 5.2, 5.3, 5.4, right, which is approximating differential equations, right? So if you guys have kind of thought back about the beginning of the semester, right, we started with talking about approximating numbers, right? Then we talked about approximating functions. Then we talked about approximating solutions to functions, okay? Then we talked about and now we're talking about approximating differential equations, right? So essentially approximating solutions to differential equations is what we want to be able to do. So let's get started. Section 5.2. Okay, will be an Euler's method. Okay. So the topics for the day. Is going to be Euler's method. Okay. And then the second one is going to be Taylor's method, which is kind of the extension of Euler's method. Right? So we have Euler's method, and then we'll talk about kind of some error analysis for that, and then Taylor's method. So let's look at the kind of this idea. And we're going to be following the book fairly closely. So if you're reading the book, hopefully you've been doing that as well as looking at some of these videos. But hopefully, again, I'll explain it well enough, hopefully, that you'll be able to understand what's going on. So let's suppose we want to determine. Let's start with an example. We wish to determine the solution to the initial value problem probably you guys use IVP for initial value problem. BVP is for boundary value problem. Initial value problem, we have some initial condition that we usually tack onto it, where we have something like this, where we have y prime equals y minus t squared plus 1. We have y of 0 is equal to 0.5. Okay. And let's just suppose we're just interested in the interval from t equals 0 to t equal to 2. Okay. So essentially my initial condition is y of 0 is equal to 0.5. And you guys are probably already familiar with this concept that we have. Essentially, this is the format that I have my function, which is y prime equals f of t and y. So I essentially have a derivative that is a function of both t and y, right? And then I have my initial condition, which is at any value in my interval that I can pick, and I usually pick the initial value, which is 0 in this case. So I'm going to say y of alpha, okay? Where alpha is just my initial value, in this case 0 here, which is equal to y sub 0. Okay. This is kind of the format of any initial value problem, at least a first order differential equation, initial value problem. So this is kind of what we have. We can put this in a little cloud. But let's go back to what we were talking about before, right? I want to be able to find a solution to differential equation, y prime equals y minus t squared plus 1. Y0 is equal to 0.5. So, seen this type of thing before. In differential equations, right, there's multiple ways of solving this problem, right? Multiple ways to do that. One way to do this is by using an integrating factor. So let's solve this problem. Okay. So first thing to do, if we want to find the solution to this problem, so let's solve. Okay. To solve this, right, if we want to use the integrating factor, or even want to do separation of variables, there's another option you can choose. I can get my dependent variable, which is y, over to one side. Okay. And of course, if I wanted to, I can use, like I said, I can use separation of variables. We're not going to do that here. Well, can we use separation of variables? I don't think we can, actually. Well, maybe we can. No, let's not do that. Let's use integrating factors. Now I'm thinking about, can I do that? Maybe we can. All right. Anyway, let's go back to this. So I want to do an integrating factor. And if you guys remember from differential equation, right? My integrating factor, which I'm going to multiply to both sides, can be found by this formula where we have p of t. This is my integrating factor that I'm going to multiply both sides by. Is equal to -1. And this -1 comes from the value that we have right here, right in front of our y, -1. Sorry, I had one of those things. And like I say, I can integrate, so my integrating factor, I call it I, is equal to e to the integral of -1 dt. Or I can write that as e to the negative t. I could do it e to the negative t plus c, but I don't need that in this case, right? The plus c is not necessary. You get the same thing if you add the plus c or not. So here's my integrating factor. I'm going to multiply this differential equation on both sides by the integrating factor. So that y prime minus y. This becomes e to the negative t times negative t squared plus 1. Okay. And then I can multiply through if I want to. But the point of the integrating factor is I notice that when I multiply e to the negative t times y prime minus y, really I can write this in a little differential form that's a little bit smaller. I can write this as the derivative with respect to t of the product e to the negative t times y, right? This is one of the reasons why we find the integrating factor. And I want you guys to notice if you do take the derivative of this product, right? Take the derivative of this product, you do end up with this when you take the derivative, which is equal to e to the negative t times negative t squared plus 1. And then I'm going to integrate both sides. Okay, integrate both sides. This is where calculators are really nice, right? If I integrate the derivative, then I get back my original function, e to the negative t times y. And when I integrate this side, right, I get on the right-hand side, e to the negative t times t squared plus 2t plus 1 plus c. And then I'm going to solve for y, so I multiply e to the negative t, the reciprocal e to the negative t, which is e to the t on both sides. So the e to the negative t's are going to cancel. So I get this. But this becomes plus c e to the t, right? Because I multiply e to the t on both sides. And I want to solve for, this is a lot of work. I want to solve for my constant here, my constant c. So we want to do that. So that's kind of our last step. And how do I solve for the constant c? Well, remember I have this initial condition that y of 0 is equal to 0.5. We know that y of 0 is equal to 0.5. So to solve for c, I plug in 0. So I'm going to use my initial condition. y of 0 is equal to 0.5. So wherever I see a t, I replace it with 0. Wherever I see a y, I replace it with 0.5. So 0 squared plus 2 times 0 plus 1 plus c e to the 0. So, well, that's some hard math, right? That's what's at negative 0.5, I think. So c is equal to negative 0.5. Okay. And so finally, I have my final solution to the initial value problem. So I'll get y is equal to t squared plus 2t plus 1 minus 0.5 e to the t. So this is our guy. And that was a lot of work, right? And now that I've solved this initial value problem, I can now plot the solution, right? I can plot the solution to this initial value problem. I don't remember what the solution looks like, but if I wanted to, I could plot the value by just, using a graph, right? I could make a little table. So I have t here, I have y of t. And this is just me just plotting 0.0 and 0.5 and 1 and 1.5 and 2, right? And I can plug 0 into this function. Plug 0 into the function, I get 0.5. If I plug 0.5 into the function, I get 1.43. So the function I'm talking about here is my solution that I have right here. If I plug t equal 1 into the function, I get 2.64. If I plug 1.5 into the function, I get 4.01. If I plug 2 into the function, I get 5.3. Right? And now I can graph this. I have a little bit of space here. I can graph this. So I have, let's say, 0.0, and then 0.5, and 1, and 1.5, and 2. Okay. And then I have my y values, right? It goes all the way up to 5.3. So let's do 1, 2, 3, 4, 5, 6, right? Not to scale, of course. So at 0 is 0.5. Let me use a different color. Use red. And at 0.5 is 1.43. So it's about there. At 1 it's 2.64. So we're about here. Okay. At 1.5 it's 4.01. Put it right here. At 2 it's 5.3. So my function is doing something like this. Here's my solution. Y of t. Okay. And if I wanted to, I can go extend this further for t equal 3, 4, 5, 6 as far as I want. I was just interested in from 0 to 2. So here I was able to solve the system, solve the differential equation, right? I found the solution, right, analytically, right, just like we did in differential equations when you took that course. And then I was able to plot the points that I wanted. But in general, it can be difficult to be able to find the solution to a differential equation. You guys we dealt with that kind of ourselves before, right? Where the solution to a differential equation can be really, really hard to find. And so this method, although it works here, may be harder if we have an even more complicated differential equation that we wanted to solve. So it'd be nice if we could be able to figure out a way to find these values of my function y without going through this process of solving for it analytically, right? Is there a way for us to be able to get a good approximation of what these y values will be, right, without going through and solving it analytically? And that's what we want to do next time, right? We want to come up with a way to do that. And the ways we're going to do that is we're going to be using Euler's method and Taylor's method to be able to solve a differential equation, at least approximate a differential equation on an interval. Without going through this whole big spiel here. All right, so that's what we're going to do next time. So I'll see you guys then.